Welcome, class. Today, we explore how math helps us handle numbers that are either extremely large, like the distance from Earth to the Sun, or incredibly small, such as the tiny diameter of a red blood cell. Imagine trying to read out loud 149,600,000,000 meters, or remember a string of zeros in 0.000007 millimeters. It's like comparing planets to tiny particles. That's where the beauty of exponents and standard form, also called scientific notation, steps in. This way, we write 149,600,000,000 meters as 1.496 times 10 to the power 11 meters, which is simpler and much neater. Similarly, very small numbers like 0.000007 meters can be expressed as 7 times 10 to the power minus 6 meters. Look at this table displaying very large and very small numbers side by side. Notice how exponents help compress these numbers to manageable forms. Let's dive in and learn how to express these numbers using exponents. Think about the last time you measured something very tiny or very big. Now, math will give you the power to express those numbers easily. Let's get comfortable with writing large numbers in standard form, also called scientific notation. The key idea is to express the number as a times 10 to the power n, where a lies between 1 and 10, and n is a positive whole number. Take 150 billion, or 150 billion meters, as an example. To write this in standard form, we rewrite it as 1.5 times 10 to the power 11. Why 11? Because if you count the zeros and digits after the first one, there are 11 places. This means multiplying 1.5 by 10 11 times. Imagine it like moving the decimal point 11 places to the right from 1.5 to get back to 150 billion. This method not only makes large numbers easier to write and read, but also easier to work with when doing calculations. Can you think of another big number you have seen, like the national debt or the distance across continents? How would you write it in standard form? Try this yourself before moving on. Now, let's handle very small numbers using standard form with negative exponents. Imagine measuring something tiny, like the diameter of a red blood cell, which can be 0.000007 meters. Reading or writing so many zeros is tiring. To convert 0.000007 into standard form, we count how many places we move the decimal point to the right to get a number between 1 and 10. Here, we move 6 places to get 7. So, 0.000007 equals 7 times 10 to the power negative 6. This means we are dividing 7 by 10 6 times. The negative exponent tells us the decimal point moves left when reading normally. This is super helpful in science, where very small numbers are common. Think about how many zeros are there in 0.00000001. How would you write that in standard form? Give it a try and see the power of negative exponents. Let's walk through an example converting a small number into standard form. Our problem is to express 0.000007 meters in a simpler and clearer exponent form. Step 1. We look at the number 0.000007 and figure out how many decimal places we move the decimal point to the right to get a number between 1 and 10. Here we move it 6 places, converting it to 7. Step 2. Because we move the decimal point to the right, our exponent will be negative. So the number becomes 7 times 10 to the power of negative 6. Therefore, 0.000007 meters can be neatly written as 7 times 10 to the power of negative 6 meters. Why is this important? It helps us write very small numbers compactly, making calculations easier when dealing with things like microorganisms or atomic scales. Ready to try similar small numbers yourself? You'll see how much simpler they become. Let's handle another practical example, expressing the thickness of a piece of paper measured as 0.0016 centimeters, using standard form. Step 1. Convert the decimal 0.0016 into a fraction to understand its meaning. That is 16 divided by 10,000. Step 2. We rewrite this as 1.6 times 10 to the power of negative 3. How do we do that? Because 0.0016 is 1.6 moved 3 decimal places to the left, corresponding to an exponent of negative 3. Hence, 0.0016 centimeters equals 1.6 times 10 to the power of negative 3 centimeters. This expression is compact and useful for scientific calculations, such as in materials science or manufacturing, where precise thickness matters. Next time you see a very small number on a ruler or a measurement chart, you'll know just how to express it powerfully using exponents. Let's dive into comparing two truly gigantic numbers. First, the diameter of the Sun. It is 1.4 times 10 to the power 9 meters. Next, the diameter of the Earth. It is 1.2756 times 10 to the power 7 meters. To compare these, we divide the Sun's diameter by the Earth's diameter. That is open bracket 1.4 times 10 to the power 9 close bracket divided by open bracket 1.2756 times 10 to the power 7 close bracket. Using the laws of exponents, this simplifies to open bracket 1.4 times 10 to the power open bracket 9 minus 7 close bracket divided by 1.2756, which is the same as open bracket 1.4 times 10 squared close bracket divided by 1.2756. Calculating this further, we get approximately 100. This means the Sun is roughly 100 times wider than our Earth. Understanding comparisons like this is crucial in astronomy to appreciate scale. Try using exponents to compare the weight or speed of other things you know. Now, let's compare two very tiny sizes, the red blood cell and the plant cell. Their sizes are expressed in standard form as 7 times 10 to the power of negative 6 meters and 1.275 times 10 to the power of negative 5 meters, respectively. To find how they compare, divide the size of the red blood cell by the size of the plant cell. That is, open bracket 7 times 10 to the power negative 6. Close bracket divided by open bracket 1.275 times 10 to the power negative 5 close bracket. Subtracting exponents in the denominator and numerator, this becomes 7 times 10 to the power open bracket, negative 6 minus open bracket, negative 5, close bracket, divided by 1.275. That simplifies to 7 times 10 to the power negative 1, divided by 1.275. 10 to the power negative 1 is 0.1. So the entire expression is roughly 7 times 0.1, which is 0.7, divided by 1.275. This is about 0.5. This tells us a red blood cell is about half the size of a plant cell. What an elegant way to compare such minuscule objects using the power of exponents. Let's solve a problem requiring addition of very large numbers in standard form. We're given the mass of the Earth is 5.97 times 10 to the power 24 kilograms, and the mass of the Moon is 7.35 times 10 to the power 22 kilograms. Step 1. To add these, we first express both numbers with the same exponent. We rewrite Earth's mass as 5.97 times 100 times 10 to the power 22, which is 597 times 10 to the power 22. Step 2. Now both numbers have the same power of 10, so we add their coefficients. 597 plus 7.35 equals 604.35. Thus, the total mass is 604.35 times 10 to the power 22. To express this neatly in standard form, move the decimal 2 places left from 604.35 to get 6.0435 and increase the exponent by 2 to 24. The final answer is 6.0435 times 10 to the power 24 kilograms. This shows how standard form helps work with very large numbers easily by handling coefficients and exponents separately. Imagine a solar eclipse where the moon comes between the Earth and the sun. At that moment, what is the distance between the moon and the sun? We are given the distance from the sun to the Earth is 1.496 times 10 to the power 11 meters. And the distance from the Earth to the moon is 3.84 times 10 to the power 8 meters. Step 1. To subtract these distances, express both with the same exponent. Rewrite 1.496 times 10 to the power 11 as 1.496 times 1,000 times 10 to the power 8, which equals 1,496 times 10 to the power 8. Step 2. Subtract the Earth to moon distance. Open bracket 1,496 minus 3.84 close bracket times 10 to the power 8, which equals 1,492.16 times 10 to the power 8 meters. Finally, writing this in proper standard form, it is approximately 1.49216 times 10 to the power 11 meters. This example demonstrates the importance of using the same powers of 10 to perform calculations with very large numbers easily. Try applying this method whenever adding or subtracting numbers in scientific notation. Let's put your knowledge to use by expressing given numbers into standard form. For the first number, 0.000035, count how many decimal places we move right to get a number between 1 and 10. We find 5 places, so it becomes 3.5 times 10 to the power -5. For the second number, 4,050,000, identify how many digits are to the right of the first non-zero digit. Counting 6 digits, we express the number as 4.05 times 10 to the power 6. This process sharpens your skill in standard form and helps you handle large or tiny numbers easily. Why not try writing other numbers in standard form to reinforce your understanding? Let's do the reverse of standard form, converting numbers in scientific notation back to usual form. First, 3.52 times 10 to the power 5 means multiplying 3.52 by 100,000, resulting in 352,000. Second, 7.54 times 10 to the power -4 means dividing 7.54 by 10,000, which equals 0.000754. Third, 3 times 10 to the power -5 means dividing 3 by 100,000, giving 0.00003. Understanding conversion. Both ways helps you fluently move between compact and expanded expressions of numbers. Try converting other scientific notation numbers to usual form to become proficient. Before we wrap up, let's refresh the powerful laws of exponents, which are crucial when dealing with standard form and negative powers. First, multiplying powers with the same base means adding their exponents. For example, a to the power m multiplied by a to the power n equals a to the power m plus n. Second, dividing powers with the same base requires subtracting the exponents. That is, a to the power m divided by a to the power n equals a to the power m minus n. Third, raising a power to another power means multiplying the exponents. So, open bracket a to the power m, close bracket to the power n equals a to the power m times n. Fourth, multiplying different bases raised to the same power equals the product of the bases raised to that power. In other words, a to the power m multiplied by b to the power m equals open bracket a times b, close bracket to the power m. Fifth, any non-zero number raised to the zero power is always 1. That is, a to the power 0 equals 1, for a not equal to 0. Finally, dividing different bases raised to the same power is the same as the quotient raised to that power. So, open bracket a to the power m close bracket divided by open bracket b to the power m close bracket equals open bracket a divided by b close bracket to the power m. Why are these rules so important? They allow us to manipulate and simplify expressions involving very large or very small numbers, especially in scientific and engineering contexts. Remember these laws and keep exploring their applications. They are your essential toolkit for mastering exponents. Let's strengthen your skills with some practice problems. First, express these numbers in standard form. 0.000000564, 0.0000021, 21,600,000, 15,240,000. Remember to count decimal places or digits accordingly. Write each in the form a times 10 raised to the power n. Next, convert these scientific notation numbers back to usual form. 2.3 times 10 to the power 4. 5.67 times 10 to the power of negative 3. Take your time to approach each carefully. Feel free to pause the video and solve them yourself before I reveal the answers. Practicing these conversions will solidify your understanding. It will build your confidence handling exponents for both small and large numbers. Today, we journey through the fascinating world of exponents and how they help us express numbers that are either too big or too tiny to handle comfortably otherwise. We learn that positive exponents, like 10 to the power 11, mean multiplying 10 by itself 11 times to represent very large numbers. Conversely, negative exponents, like 10 to the power negative 6, mean dividing by 10 6 times to represent very small numbers. Scientific notation is key in various real-world fields. Astronomers calculate vast distances between stars. Biologists measure microscopic cells, and engineers work with incredibly precise dimensions. By mastering this, you have a powerful way to compare and perform calculations across wildly different scales without getting lost in zeros. Keep practicing these methods, and soon, reading and working with any size number will feel as natural as counting your fingers. Thank you for your enthusiasm today. Keep the spark alive in exploring the infinite scales around us through mathematics.